there any questions on the course? Everybody's okay? Everybody's understanding sort of how it's going to work? Okay. So what I like to do maybe with some of the time here that we have left in lab is just kind of review some of those topics, maybe from first semester, that again, we may see not exactly the same as what we saw maybe in first semester, but it will tie into a lot of sort of things that we do in calculations, just to make sure everybody's on the same page. I think I'll also probably post up on Canvas the next day or so, maybe some review type information on some of these topics. Again, if you want to kind of look through that to help you out, with this class. So let's just sort of talk about some of the important first semester topics. I guess it is a chemistry class and a science class, right? So we might as well make sure that we do talk about, I guess, some of the real basics as well. So, for example, significant figures, right? Remember that when you do give an answer in chemistry and in science in general, right, you do always want to give the answer to the right number of significant figures. And there's rules for counting significant figures, which I hope you remember. Pretty much we'll just kind of go over those fairly quickly. Any non-zero, right, is significant. And then we do have our zeros, which there's three different types. We have leading zeros. Those are not significant. So those would be zeros like this. And we keep going until we hit that first non-zero, right, when we start counting. So this guy would have three significant figures. We do have zeros that are sort of between two non-zero numbers. And those are significant, right? So you got like 1, 0, 0, 1. These zeros here that are trapped would be significant. That would have four significant figures in this case. And then really the zero that gives most people the problem is the zeros at the end. And those may or may not be significant. And what determines if they are significant is a decimal place or decimal point. So if there is a decimal point, yes, there is, then the zeros would be significant. If there's no decimal point, they are not significant. So if you had 100 written like that with the decimal point, that would be three significant figures. If you had 100 written like that with no decimal point, that would be one significant figure. So again, hopefully you remember significant figures. You should always try to, even in this class, obviously, give the right number of significant figures when you give an answer. Most importantly, though, when we do multiplying or dividing, the answer should have the same number of significant figures as the number with the least number of sig figs. So again, if we took 125 and we multiplied it by 0.1002, we are multiplying this as three significant figures. This guy's got four significant figures. That means our answer should end up with three significant figures. So it's always the one with the least number, multiplying or dividing. And if you add or subtract, which is sort of the other operation that you could do, we look at the number of decimal places. and is still the one with the least number of decimal places. So your answer should have the same number of decimal places as the number with the least. So if we took 3.256 and we added it to 1.4, this would be 6564. This has 3 decimal places. This has 1 decimal place. We should round to here. We then should round up because of the 5, and we should end up with 4.7 in that particular case. Any questions on Sig Figs or anything like that? Also, really important in terms of numbers is sometimes we deal a lot, especially in this class, with a lot of large numbers, a lot of small numbers. So as you're familiar with, hopefully, right, you use scientific notation for that. Scientific notation has a general formula n times 10 to the n. This is a number between 1 and 10, not 10, 20, 30, 100, or not less than 1. That is a number that is either positive or negative, depending on which way you move the decimal point. So obviously, if you had 3, 2, 5, 6, we would go 1, 2, and 3 places that way. 3.256 times 10 to the 3, 0.00356. We would go 1, 2, and 3 places that way. 3.56 times 10 to the minus 3. Negative exponent, small number. Positive exponent, larger number. Also important is Sig Figs. That has 4 significant figures. This guy has 3 significant figures. And when we write a number in scientific notation, all the numbers before the times 10 part are significant. So when we have a number in scientific notation, all those numbers that come before that times 10 part are significant. And that means that this guy actually does have 4 significant figures when I write it that way. And this guy's got 3 significant figures when I write it that way. Any questions on that there? Also, more importantly than actually knowing what it is in scientific notation is actually on your calculator and how to properly punch numbers in scientific notation. I'm amazed at how many people actually don't know how to properly do that. So I think they're never taught really how to properly do it with their calculator. So it's super important, especially in our class, to make sure that when you have a number in scientific notation, that you actually put it into your calculator correctly. So let's talk about calculators. Usually there's 2 really popular exponent buttons. A lot of calculators will have an EE button. Some calculators will have an EXP button. Some of the newer calculators may actually even have a button that's times 10 to the n. And if you have this button, you usually will also have like a little circle guy that's kind of like a control panel there on your calculator as well. And if you do have that button, I'll tell you what you need to do in just a second. But we'll first focus on these 2 common buttons. Those are your exponent buttons, which means when you have a number that's in scientific notation, you want to always use your exponent button when you punch it in. By the way, a couple other important buttons is your negative button, which sometimes looks like this, or your positive, negative, not the subtract button, oddly. So don't use the subtract button. So let's just say we have 3.25 times 10 to the negative 6, and we wanted to basically enter that in our calculator in scientific notation. We would actually put 3.25. At this point, you would put your exponent button. And on a lot of these calculators, if you do that, you'll have 3.25, may pop an E there, may go like 3.25, maybe pop a couple of zeros up on top or something like that. When you hit this button, that represents this part of the number, which means that you should not be hitting the multiplication button. You should not be hitting the second log button like most people do. You should not hit the shift log button or any of those things. So when you hit that button and it puts up that E or the 2 zeros, that represents the times 10 part. Because this is a negative exponent, again, we would want to hit our negative button, whichever one that is, not the subtract button. And it will probably put a negative here in front of the E. It will probably put a negative in front of those 2 zeros. And then lastly, we would put 6 and would put this, and it would turn this guy into a 6 at that point. And this is what proper scientific notation looks like when you punch it into your calculator. If you are still putting the multiplication button, you're doing like the second and log button, you know, that little guy over log, which most people think is their like exponent button, and it's actually not. We will actually use that button later on in the semester. This is the proper way to do it. If you have that EXP button or EAE button, you can push it in just like that. And then if you needed to say divided by 1.2 times 10 to the 22, you would then hit the divide button, 1.2, again, your exponent button, and 22. Just to make sure you get the right answer, I will punch it in. I made it up, so we'll make sure we're all on the same page here as well. You're welcome. You're not the only one. Nobody usually teaches people how to actually use their calculators correctly, especially with scientific notation. People always punch it in incorrect. And a lot of times people are always frustrated with that, because what usually happens when you do punch it in incorrectly in your calculator is you actually get a number that looks almost right, but it's just slightly off. And that's usually frustrating for a lot of people. So 3.25, again, exponent button, negative button 6. We want to divide by 1.2, exponent button 22. And on my calculator, I do get 2.7 on my rounding here. And you don't want to forget it. So again, on my calculator, I got a bunch of numbers. And the other very common thing that people do, like on my calculator, shows up something like this. And people forget about this part of the number sometimes. So again here, 3 significant figures divided by 2 significant figures should get us to 2 significant figures times 10 to the minus 28. Again, that's what the E minus 28 means on your calculator. Don't forget that part when you write it. And when you do write it, you should write it like I just did there, times 10 to the minus 28, not E to the minus 28. So that's not really proper way of writing scientific notation, even though that's kind of how we do it on calculators. So when you do, don't forget that last part of the number. Make sure that you do sort of write it correctly. Again, like I was saying before, what typically will happen if you're punching these things in wrong is the front part of the number here, it's all good, but this part will be off by a little bit. And that's usually the way you're punching it in. Now, if you do have a kind of a newer calculator that has this button here, and like I said, it usually will have this sort of circle here as well. You pretty much do the same thing. The only difference is the way these newer calculators are programmed. I don't want to say they're programmed wrong, but they're programmed wrong for like how people use them. So if you don't put parentheses around all your numbers, you're going to be in trouble. So for example, if we were doing this same problem and you have really that guy as your button, so if we're still doing this guy, what you would need to do is actually start with a parentheses, hit 3.25, and then you would actually hit your times 10 to the end. And when you do that on your calculator, what will happen is it will go 3.25. It will probably actually say times 10, and then you'll have a blinking cursor up there on top. And at that point, again, you would want to hit your negative button and 6. And what will end up happening is at that point, it will go 3.25. Obviously, there's a parentheses there, times 10 to the negative 6. And your blinking button will still be up on top. And that's where this circle guy comes into play. You need to hit the right-hand side of it, and that will bring your blinker down, basically, when you do that. So you usually got to hit that little circle part. And I'll bring it down, and then you could close the parentheses at that point. And then you basically need to type in the other number the exact same way, again, using those parentheses around every number that you put in there in scientific notation. Otherwise, again, your calculator will most likely do the calculation wrong for you. So again, you would have to punch it in the exact same way. In this case, actually, it would be 22. And then you would have to hit that circle on the right, close the parentheses, and then hit equals. So perfectly fine. Again, a lot of newer ones do have these two guys. But the only difference is you got to put a lot of parentheses around the numbers. Otherwise, if you leave those parentheses off, what will typically happen is you'll get the wrong answer. Now, if you have the EE button or the EXP button, you're good. You don't have to put parentheses around anything. You can do as many numbers as you want. They're programmed, they'll say correctly. They're programmed correctly. You could do as many numbers as you want. You won't run into any problem. So more importantly, again, in terms of scientific notation is really this part of it. And we definitely for sure will have to be punching these numbers in, or a lot of numbers in scientific notation. So you want to make sure that you do always, when you have an exponent or really a number in scientific notation, always use your exponent button. Otherwise, again, you will usually find yourself pretty close to the right answer. Again, that front part's usually pretty good, but this part's usually the part that's off. And again, if you're finding that is an issue for you as we go through, just make sure at some point you maybe touch base with me and we'll try to figure it out on your calculator how to properly kind of punch it in. Any question on those three sort of common ways to do scientific notation? All right, so again, that's something that, they really should teach you in Chem 50, but sometimes people don't actually teach you. They teach you the part about scientific notation, how to write it, but a lot of times people don't teach you like actually punch it in correctly. So it's really important to make sure you do that. The other couple of things, just a reminder on some of these really basic things here is your calculator doesn't always give you the answer to the correct number of significant figures, obviously. And obviously, depending on how your calculator is programmed, you may not always get the answer in scientific notation. So you could convert it to scientific notation or tell your calculator to do it for you. So those are a couple of things to sort of keep in mind. Other important things, again, we probably don't do a ton of it in this class, but just a reminder that molar mass, right? Molar mass has units of grams per mole. We can typically find the molar mass of an element off of the periodic table. So when we look at something like hydrogen, right, that is 1.008 grams per mole of hydrogen is the molar mass. If we had something like water, we would also look up oxygen that's on the periodic table. And again, that's the atomic mass, also the molar mass. And that basically means there's 16 grams per mole of oxygen. So if we had something like water, we add up all the parts. And that would get us our molar mass of water, which is 18.02 grams per mole. Molar mass is really like a conversion factor, right? That you could go from grams to moles or backwards. And to do that, we use the molar mass. Remember that when we do something like this, we could also flip it around and use it like the moles on top, the grams on the bottom. When we typically do calculations in chemistry, right, we show calculations using what is referred to as dimensional analysis. Dimensional analysis is a fancy way of saying showing the calculation with all the units canceling in the setup. So for example, if I had 325 grams of water and I want to know how many moles that is, to properly set it up, we would start with the 325 grams of water. Although it's not written as a fraction, it technically is over 1. And dimensional analysis is, again, a way that we use units to cancel things out. We would use the molar mass in this form, where the grams have the number and it's 1 mole. Moles of water would go up on top. The 18.02 grams of water would go on the bottom. We're basically multiplying what's on the top and we're dividing by what's on the bottom here. So we're basically dividing grams of water divided by grams of water, so they cancel each other out, just like when you divide 2 divided by 2, it equals 1. And we're basically going to take 325 times 1 divided by 1802. So 325 divided by 18.02 gets you again here 18.03551609 units are moles of water. Significant figure wise, this is considered an exact number. You don't have to worry about it. Sig fig wise, that is 3 significant figures, which means we should take it to about here. That would get us 18 moles of water in this case. This is, again, the way you should be showing calculations, right? This sort of dimensional analysis way. Some people use that approach when you're taught. Some people do like the, somebody called it a railroad type move, like that type of thing. I don't know. But, you know, however you do it, you do need to do it sort of dimensional analysis way on most calculations that we do, especially with some type of conversion where we could clearly see the units sort of canceling each other out. So again, molar mass, getting it from the periodic tables is really important, sort of understanding of stuff that we do. Any questions on that there? Also, as we sort of talked about before, types of reactions and being able to write equations is really, really important in this class. A reminder of the general setup of equations. We have reactants, which are on our left-hand side of the arrow, going to our products there on the right-hand side of the arrow. And the reactants are our starting material. Our products are obviously what are formed as a result of a chemical reaction. When we use equations, it's very important that they should always be balanced. Now, for the most part, if you're given an equation, probably in this class, it's probably going to be balanced, but you should check it. We balance equations, a reminder, by balancing the coefficients, the numbers that come in front, right? So if we had some H2 plus some O2, giving you some water, we are not balanced here, right? We have 2 hydrogens on the left, we have 2 oxygens on the left, while we have 2 hydrogens on the right and only 1 oxygen. So to fix that, we would put a 2 in front of the water, giving us 4 oxygens and, I'm sorry, 2 oxygens and 4 hydrogens. That then needs to balance the hydrogen on this side by putting a 2 there. And again, these coefficients are what we use, right, to balance the equation. Conservation of mass, right? We don't lose any elements along the way in a reaction. Basically, we're just breaking apart bonds and reforming new bonds on the other side. So that's really important. As we talked about before, the idea of actually, in a lot of cases, you do have to sort of come up with the reaction. So perhaps you're just given the reactants, you need to come up with the products. So you do need to be pretty efficient at being able to actually write a completed equation and actually balance it as well, obviously. So just a quick review of the different sort of types or classifications of reactions that, you know, hopefully you've seen before, or if not, I guess you will see now, I suppose. You know, we have a combination reaction, sometimes referred to as a synthesis reaction. And that is basically when we put something together, like A plus B basically makes A and B. Kind of like what I just wrote up there on top, our water example. The water coming together, 2 things make 1 thing. Again, a combination reaction. You know, something like magnesium and oxygen. Perhaps you've done this experiment or seen this experiment. You burn magnesium in a Bunsen burner or something like that, or a flame. It gets very, very bright, and it makes basically 2 things make 1 thing. Sort of the opposite of that is a decomposition reaction. And that's basically where we take 1 thing and we basically break it apart into maybe 2 or more things. So sort of an opposite there. So decomposition, you know, something like, excuse me, We take some lead-4 oxide and we break it apart into some lead oxide, lead-2 oxide, and some oxygen. I think a 2 maybe there as well. Again, one thing breaks apart into a couple of other things there. So combination basically puts it together. Decomposition basically breaks it back apart. They're really opposites of each other, right? So one puts it together, one breaks it apart. Any question on those two? Now, another type of reaction is a single replacement reaction. And these are common reactions. This is where you have like A plus B, C. And usually this is either a metal or a non-metal. And this is usually an ionic compound, so something with a positive, negative. And if this guy, if A was a metal, typically what will happen is the metal will come in and kick out the positive guy, because metals become positively charged, although it doesn't have a charge at this point. And a new ionic compound would form, and the B would come out with no charge on this side. And if A was a non-metal, the opposite would happen. It would actually come in and kick out the negative guy. Non-metals typically are negatively charged, right? When they do have a charge. Has no charge here, by the way. No charge. And we do get a new ionic compound in this case, and the C would come out again with kind of no charge here. Perhaps you remember these type of reactions. These are reactions where, sometimes if hydrogen is replaced, sometimes we'll produce hydrogen gas, bubbles, hydrogen displacement. So something like zinc, for example, and some hydrochloric acid. Again, this has no charge. As a positive, negative zinc submetal, so it'll come in and kick out hydrogen. When it does so, we will get zinc chloride as it comes together. The zinc actually gains a +2 charge at that point. Chlorine is -1, and our hydrogen comes out as molecular hydrogen, no charge, as a gas. So if you ever done this one or seen this one, that's where we see bubbles start to form and stuff like that. We also, again, could have like a halogen sort of deal. If we had Cl2, remember our halogens, which is group 7 on the periodic table, typically come as diatomic molecules. And again, here, this is a positive, negative, no charge happening here. The chlorine, which is a nonmetal, will kick out the nonmetal in this particular case if this reaction takes place. And we will get the sodium and the chlorine coming together. And that would not be a 2 there. Sorry about that. We get this NaCl plus the Br2 coming out. And again, we make a new ionic compound. And again, our nonmetal comes out. These are, again, in order for this reaction to happen, whatever is coming in. So when A is coming in, it needs to be more reactive than what it's replacing. And if it's less reactive, then the reaction would not take place. So for example, if you substituted, say, copper in place of the zinc in that first one, copper is less reactive than hydrogen, it would not take place. Years ago in Chem 50, they used to do an experiment with pennies involving this. I don't know if they do that anymore, but they used to years ago. But it usually led to something you might remember, an activity series. And maybe if you remember an activity series of metals, basically hydrogen in the middle, a bunch of metals sort of listed above, a bunch of metals listed below. Anything higher on the list is more reactive than anything lower. So higher on list, more reactive than lower on the list. And anybody lower on the list is less reactive, obviously, than anybody higher on the list, which means if you're lower on the list, you won't replace it. And if you're higher on the list, obviously, you would replace it. So, for example, zinc would be found above hydrogen, and copper would be found below hydrogen. and it wouldn't do that replacement. We also see these three types of reactions is sometimes classified in a big category that you hopefully talked a little bit about in Chem 50. If not, we'll talk more about it in a later chapter. But these are also sometimes referred to as redox reactions, perhaps. Yeah. So redox reactions are oxidation reduction reactions. And basically, in oxidation reduction reactions, if something goes through an oxidation, one definition is that it loses electrons. And when we lose electrons, usually it becomes more positive. And a reduction, if something goes through a reduction, it basically will gain electrons. Again, is one sort of definition. And usually, obviously, you become more negative in that case. Sometimes people remember that as Leo the lion goes grr. Loss of electron oxidation, gain of electrons reduction. Some people remember that as the oil rig. Oxidizing is losing, reducing is gaining. So basically those three types of reactions we just talked about, the synthesis, the decomposition, and really the single replacement reactions, those all really fall under the kind of the big umbrella of redox reactions that we commonly see. Any questions on that there? Another really important sort of classification of reactions, and ones that we really do kind of see a lot in this class. We will see some of these single replacements and stuff like that when we talk about the redox chapter a little bit later on. I think it's maybe chapter 18 or something like that. We'll revisit redox reactions, but up front, a good important type of reaction that we oftentimes do come across in this class is the double displacement reactions. So double displacement reactions are also sort of a big classification of reactions. And in a double displacement reaction, it has this general form of AB plus CD. This is positive, negative, positive, negative. And basically, when we have a double displacement reaction, what ends up happening is the two positive guys pretty much switch partners. So what we end up getting is two new ionic compounds on the other side. And an ionic compound, again, a reminder, is a positive and negative guy, right? Held together by no sharing of electrons, but the electrostatic attraction between the positive charge and the negative charge is what holds those guys together. And again, this is essentially what happens. And under sort of this classification, this is where we find things like precipitation reactions. And basically, if you take something like, say, silver nitrate plus some sodium chloride, again, positive, negative guy, positive, negative. These two guys swap partners. We end up with some silver chloride plus some sodium nitrate. Based on solubility rules, if you remember some of those things, which would be good as well as we go through this semester, silver chloride is insoluble based on solubility rules. Things like chlorides, bromides, iodides are insoluble in are soluble in everything except silver, lead, and mercury 1. So this, because it's silver, means it's going to be a solid. And this is a precipitation reaction because it basically makes a precipitate. Everything else here is aqueous. Aqueous means basically a solution, a water environment, no solid involved. And this is what's sometimes referred to as well as a molecular equation. And if you remember talking about double displacement reactions, also remember talking about perhaps precipitation reactions. You know that in solution, you could also represent this reaction another way by breaking up all the ionic compounds into their ions, because that is really what's happening when they're in solution. So something like silver nitrate would break apart into a silver ion and a nitrate ion. Sodium would break apart into a sodium ion and a chloride ion. Anything that's a solid, anything that's a liquid, anything that's a gas will stay together. It will not break apart because it's really not ionic. So our solid here would stay together. And we would also be left with a sodium ion on the other side. And just get this out of my way here. And a nitrate ion that's happening there as well. And you might recognize perhaps an equation such as this. This is sometimes referred to as the total ionic or complete Ionic equation. And it's really an equation that's written, especially with double displacement reactions, to basically describe to us what is truly happening sort of in that beaker as stuff is sort of floating around. When you write a total ionic equation, you might also remember that if you look on both sides of the equation, you will find some ions that look exactly the same. So for example, there's a nitrate on both sides. There's also a sodium on both sides. And when you have ions that are on both sides of the equation, those are what are referred to as spectator ions. Spectator ions are pretty much what it sounds like. If you're a spectator, you're not really doing much other than watching. They're really just there to balance out charges and stuff like that. So a lot of times in chemistry, we treat the arrow like an equal sign in math. So because they're on opposite sides of the arrow, they will actually cancel each other out, kind of like you subtracted it to the other side. And what you're left with is really what's happening in a particular reaction. You have the silver ion going and finding the chloride ion to make this white solid, which is our silver chloride. And this is what is sometimes referred to as the net ionic equation. So we do come across writing some net ionic equations a lot in this class. Some may look really much like this. Some may look sort of like a version of this, but the net ionic equation is an important one because, again, it basically does really cut to the heart of the matter of what is happening. It explains exactly sort of what is reacting in this particular case. So a precipitation reaction would obviously make it precipitate based on solubility rules. And obviously, it is ultimately a double displacement reaction. But sometimes, again, we get to the heart of the matter by writing the net ionic equation, which basically describes exactly what's happening in this case. Any questions on that there? Now, another reaction that definitely we see a lot in this class is also really a double displacement reaction. It is sometimes referred to as an acid-base reaction, or maybe an acid-base neutralization reaction. And this is one we definitely, especially in those chapters of 14, 15, come across a lot. When we take an acid plus a base, typically we make two things. We make water and a salt, right? A salt, again, it's just an ionic compound. You know, so if we take some HCl, which is hydrochloric acid, plus some sodium hydroxide, which is a strong base, although it really is still a double displacement reaction, that's positive, that's negative. Our two positive guys will switch partners, making H plus and OH minus. That is where we get our water from, and our salt here being our sodium chloride in this particular case. This is a basic reaction that happens, and we see a lot in here is acid-base reactions. I mean, we have pretty much 2 chapters almost dedicated to these type of reactions, so we definitely see this reaction occur a lot. In addition, why they're sometimes called, again, a reminder, as neutralization reactions, because This is the molecular equation, and if we were to break this apart into the complete ionic equation, our guys would break apart. Again, water being a liquid would stay together. Our sodium ion would break apart, and our chloride as well. That gives us our spectator ions of sodium on both sides, also chloride on both sides. And those guys would cancel out, leaving us our net ionic equation, which is pretty much always what happens when you take a strong acid, in this case with a strong base, is basically the H plus from the acid goes and finds the hydroxide from the base, and we make water, which is why it's sometimes referred to as a neutralization reaction. A reminder, though, that when we do write things like net ionic equations and total ionic equations, it does really involve things known as electrolytes, right? And you also maybe remember electrolytes. There are strong electrolytes, which are things that 100% break apart. There's also weak electrolytes, which mainly stay together in solution and do not break apart. So, for example, if we took HF, which is hydrofluoric acid plus some sodium hydroxide, it would still do the same reaction here. We would still have our water that's being formed, and our salt here would be NaF. The difference, though, is this is really a weak acid, which is a weak electrolyte, which means when it's in solution, it actually stays together mainly. So it doesn't really break apart. And if we were going to the total ionic equation and then the net ionic equation, you actually would keep it together. You would still break apart sodium hydroxide, which is a strong base and a strong electrolyte. The water would stay together. The sodium fluoride would break apart. And in this particular case, the difference by having that sort of weak electrolyte or weak acid in this case there is, it's actually only the sodium here that's going to basically cancel out. And what we're left with is the HF plus the hydroxide, making some water here and our fluoride ion. So, we do get a slightly different thing depending if something is a strong electrolyte or a weak electrolyte. And that definitely comes into play, especially when we talk about acids and bases. We're going to talk about strong acids, what happens. We're going to talk about strong bases and weak acids. So we do see a lot of sort of these type of reactions occur. And again, it's super important to be able to actually write these equations as we go through them. So, as we talk about these different topics, you want to make sure that you really have the basis understanding of, when I'm just given like these two things, am I able to really get what comes out on this side? Am I able to write what comes out on that side? And if the answer is no, you definitely need to kind of work on that, because it is going to be problematic for you as we go through these different chapters. If the answer is yes, I'm good, I can kind of figure these things out, you're going to be in pretty good shape, And again, it may not seem like a really big deal that being able to sort of write the equation, but it really is in certain chapters, because if you write an equation incorrectly and you look at it, it's going to tell you in your head that you should be doing this type of calculation based on the equation. But because it's the wrong equation, you actually should be doing the opposite calculation. So it is really, really important to, understand how to write these equations, and especially just starting with, what's given to you. So just the reactants a lot of times and a lot of problems, that's all that's given to you. And you're not even given, a reaction. You're sometimes not even given two reactants. You're just given, hey, you have some sodium fluoride. What's the pH? And you need to be able to know, when you have sodium fluoride, how to come up with the reaction, what it's going to react with, what it should produce and stuff like that. And some of that we will talk about, obviously, as we go through those chapters. But when we do talk about it, make sure you really do pay attention, because it can really help you in the calculation part. Like I said, there are going to be absolutely problems where you're just like, you're going to be given, hey, you have a 0.15 molar sodium fluoride solution. What's the pH? That's it. That's like all you're given. And you need to be able to turn that, to answer this correctly, you need to be able to turn that sodium fluoride into an actual equation and then use the equation to solve the problem. So it's a big roadblock for a lot of people when they're in this class is actually that part. And a lot of times students are like that. People are like that. You hit a roadblock and you're like, I'm not really sure where to go from here because I don't know where to go from here. And sometimes that is this like almost starting step, and you don't want to hit those sort of roadblocks, sort of right off the bat. Any questions on that there? Our equations. And again, specifically when we do talk about these topics, we do talk about the equations. I do show you sort of as we go through examples, when you're starting with this is sort of the equation you should, end up with. So you'll be able to see those. But again, sometimes people just sort of gloss over that part and they just focus more on the numbers and the calculation. So again, it's really important to make sure that you do pay attention to that part of it. Some other sort of topics, again, stoichiometry in general. I don't want to say we don't do a ton of it, but it does pop in again. And just some of the ideas behind stoichiometry. Stoichiometry, again, in case you're not sure what that is, I hope you are, but that's 2a plus 3b, say, goes to 4c. Stoichiometry is a way that we use the balanced equation and those coefficients and basically this stoichiometric equivalent. So from an equation like this, we could say that for every 2 moles of A, we get 3 moles of B. We got to throw in there. For every 2 moles of A we throw in there, we should get 4 moles of C out. And it's really just the coefficients. Every 3 moles of B we throw in there, we also get 4 moles of C out. And for each of these sort of stoichiometric equalities, right, you could write 2 conversion factors, 2 moles of A over 3 moles of B, are 3 moles of B, for example, over 2 moles of A. And you obviously could do that for each of these sort of coefficients or equalities. Why do we use it? Is because in certain stoichiometry problems, we may just be told, hey, we're starting with 4 moles of A. How much C would we produce, right? How many moles of C, for example? And we basically use stoichiometry. It's really just a fancy way as a conversion factor. And where we get the conversion factor from, right, is the balanced equation rather than looking it up on a table. So if we were to do a problem like this, we would go 4 moles of A, again, doing sort of our dimensional analysis. If we want to know how many moles of C, we would want to use this relationship here. Again, opposites cancel. So 2 moles of A would go on the bottom. 4 moles of C would go up on top. Moles of A would cancel. We take 4 times 4, which is 16, divided by 2 gives us 8 moles of C would be produced, right? And that's a basic stoichiometry problem. Obviously, a lot of times we start with grams before this. So sometimes we go grams, 2 moles, again, using the molar mass to do that. And sometimes at the back end here, we want to know how many grams. So we would obviously use the molar mass if we knew what it was to do that as well. So that's sort of a basic stoichiometry problem here. When we do figure out how much is produced in a reaction, that is what is sometimes referred to as the theoretical yield, right? The theoretical yield is how much is produced based on the reaction, based on the equation, based on the idea that everything went perfect. You didn't spill anything. You weren't a klutz and dropped everything on the ground and dropped all your beakers in the trash or anything like that. Based on the equation, based on how much you started with, that's how much you should get. Also, you might remember something known as the actual yield. The actual yield is pretty much what the title implies. It's actually how much you got. So the actual yield is when you physically do the experiment, that's how much you actually produce. And usually we put those together to calculate something known as the percent yield, which is our actual divided by our theoretical times 100%. So those are common things that we get out. Truthfully, not a lot of that, probably too much in here in 51, but the idea of sort of stoichiometry is important. The other sort of important idea about stoichiometry is the idea of limiting reagents, right? So we do have limiting reagents, we do have excess reagents, sometimes called reactants. So the idea of limiting reagents or reactants. Limiting reagents also goes with excess reagents. So the limiting reagent is really the reactant that gets used up first. In a chemical reaction. Well, obviously the excess reagent you have plenty of, it doesn't get used up. Why are these things important? Well, hopefully you remember that it is always the limiting reagent that determines how much product you can make. So it's always that limiting reagent that actually determines how much product you would produce. Also, a couple of reminders. How do you know you need to figure that out? Is because usually in limiting reagent problems, you're given the starting amount of both reactants. And what does that mean? It basically means that you have enough information for both of those guys to get to the number of moles of each of them. So if you are given enough information, be that grams of each of them, moles of each of them, volume and molarity of each of them, pressure and all that kind of stuff if they're gases, but you're given enough information to basically figure out the moles of each of those. You need to first figure out which one's the limiting reagent, and that will determine how much product did you make. Now, I won't go into how to figure out the limiting reagent because there's multiple ways that you could do it depending on how you were taught. Most common way a lot of times is you just do two separate stoichiometry calculations, and whichever reactant individually produces the least amount of product, that would be your limiting reagent. Another very common way is to do a stoichiometry calculation where you figure out how much of the other reactant you need to use up all the first guy and see if you have enough. A third common way is to do an ice table approach. So there's a lot of different ways you can kind of figure that out. Hopefully you remember one way to figure that out. And again, I don't know if we will directly be doing a lot of limiting reagent calculations, but again, this is more where sort of theoretically in the theory of the idea of limiting reagents does pop up a lot in some of the stuff that we do. So, again, I don't know if we'll be doing a ton of straight limiting reagent type calculations, but really more so for us probably is that understanding that when we're trying to figure out how much is being produced, we do want to look at whichever one's sort of the limiting aspect of it versus the guy that's the excess part of it. So that definitely does pop up. Like I said, maybe not so much direct calculations, but you should still obviously know how to do that. Question on stoichiometry. So another really sort of big topic that definitely we see a lot of that hopefully you've talked about before is our good friend solutions. Yes. So when we talk about solutions, solutions usually has that aqueous symbol next to it. And just in case you're not sure or never were really taught what is really the difference between the L and the AQ, there actually is a difference between those two symbols there. L is a pure liquid, which basically means if you take just some water by itself, that's a pure liquid. There's nothing else in that water. Now, if you take water, which is a pure liquid, and you add some solid sodium chloride to it, those two guys, the solid sodium chloride will dissolve in the water, and you will end up with a sodium chloride solution, which would give you the aqueous symbol. So the aqueous symbol basically means a water environment. It is usually made by taking a solute, which is the smaller part of the solution. So this guy is sometimes referred to as the solute. and dissolving it in a larger part of the solution, which is sometimes referred to as the solvent, right? So the solute is the smaller part, the solvent is the larger part. A lot of times the solvent is water. It does not always have to be water 100% of the time, but water is a very good solvent, as you might have talked about, because it is polar. Works really well with polar guys, works well with ionic compounds because of those intermolecular forces. So it works really well with it. Now, when we put it together again, that aqueous basically, that is the two parts to a solution, your solute and your solvent. So again, there is a difference between, when we talk about something that's a pure liquid versus something that's aqueous. The good news is the name of the solution is always the solute. So if you have a sodium chloride solution, the solute is sodium chloride. If you have a potassium fluoride solution, it is potassium fluoride as the solute. So the nice thing is it's always the name, and you will definitely kind of know what the solute is. Now, when we talk about solutions, very important is the idea of concentration. Now, there's a lot of different concentrations that you probably talked about in Chem 50, things like percent mass to mass, percent mass to volume, percent volume to volume. You maybe even talked about, molality, which is little m, which, by the way, is moles per kilogram of solvent. Maybe at the end there, we talked about colligative properties. But the big one is big M there, which is molarity. Molarity is moles of solute per liter of solution. And molarity is really the one we deal with a lot, obviously, in here. We do a lot of things with solutions, and we're given concentrations, which is, again, molarity, that big M, which is moles per liter. A reminder that you can rearrange this and solve for any of those three things. So if I want to know the liters, that would be the moles divided by the molarity. If I wanted the moles, that would be the liters times the molarity. So again, we are in this class using molarity to solve for, any of these things. So that is a very common way. It's also, as you can see here, like I was talking about earlier, a very common way to get the moles of something is to take the liters times the molarity. I would also recommend, as maybe your teacher told you in Chem 50, that when you're doing calculations, if you have like a 4.5 molar sodium chloride solution, that's what the big M stands for, molar, it's good to get rid of the big M and use both units. So that basically means you have 4.5 moles of sodium chloride per liter. The number always stays with the moles, and it's always per 1 liter. You also can think of it like a conversion factor, and you could use it the opposite way, like in a dimensional analysis type situation, and put the liters up on top, the moles on the bottom. So, for example, if we had 52 milliliters of that 4.5 molar sodium chloride solution, and we want to know how many moles that would be, we can do sort of a problem to calculate that, again, using basically this as like a conversion factor and sort of dimensional analysis. And the reason why you want to kind of use both units is, I can't tell you how many calculations I've seen where people leave the big M and have no clue where the liters is. They're not sure if it's on top, it's on the bottom, it's there even. They just have no idea. So always good to use both of those units. You can clearly see the units. Also, because you could clearly see the units, you will know that that milliliters is not going to cancel. So we do need to convert it into liters. So that is definitely a conversion we do a lot, which is 1,000 milliliters is 1 liter, or move the decimal point a few places one way or the other. So we would take 52 divided by 1,000, and that's going to give us 0.052 liters. Now that we have it in liters, we can use our molarity that was given to us. Again, setting it up dimensional analysis so you could kind of see everybody cancel. Moles per liter of our sodium chloride. Again, liters will cancel. We're going to multiply here. The 0.052 times 4.5 gets you 0.234 moles of sodium chloride. And in this particular case, probably two significant figures based off of that first number there. And we'd probably take it down to 0.23 moles of sodium chloride. So that's a very common sort of calculation that we do a lot, especially when dealing with solutions, because when we're dealing with solutions, we're not oftentimes talking about grams and weighing out grams or anything like that. We're talking about actually, measuring out volumes and how much we're doing. Any questions on sort of that type of calculation there? Since we're talking about sort of measuring out volumes and stuff like that, a reminder that when we do take a reading using something like a very badly drawn graduated cylinder here, sort of looks like it maybe. You always want to look at sort of the scale. So if that's a we'll go with 20 on that, and we'll say these are milliliters. So when we do have a liquid that's in sort of a glass container, you usually will see that curvature of the liquid, right? That is the meniscus. We always take a reading from the bottom of the meniscus. I'm a very badly drawn one here, but always want to read from the bottom of the meniscus. Again, sometimes it's really easy to see that curvature. Sometimes, depending on your glassware, not so easy to see the curvature, but you always want to kind of shoot from the bottom of the meniscus when you're trying to take a volume reading. Also really important to look and see on the scales, what does each represent, right? So that is 10 milliliters. That is one line, 2 lines, 3 lines, 4 lines, 5 lines, 6 lines, like 7 lines here, 8 lines, 9 lines, and 10 lines. So there are 10 markings between 10 and 20. That means in this case, each of the smallest markings is 1 milliliter. That would be 11, that would be 12, that would be 13, 14, 15, 16, 17, 18, 19, and so forth. So you want to look and see where you're at. So my really badly drawn kind of looks like I hit 17 on the nose. We'll go with that. So I would definitely want to write 17 milliliters. Yes. No, that would be wrong. Yes. So because I have the ability on this guy to fall kind of between the two numbers, typically speaking, you could go one more place to the right of that smallest marking, which means even if I hit dead on 17, if I feel like it, because I have the ability to do so, I really should record 17.0 milliliters in this particular case. Why would that be important? Well, it's important really because of significant figures like we talked about last time, or a little bit earlier. If you take that value of 17 milliliters versus 17.0 milliliters, when we record a measurement, perhaps you remember you record all the certain numbers plus the first uncertain number. And that's basically the definition of what significant figures are. So when you take a measurement and you record all the certain numbers plus that first uncertain number, you're basically recording all the significant figures. So what does that certain number means? It means no matter who takes a look at it, they're going to pretty much agree with you that it is at least that. But there is always some type of estimate that is made when you take a measurement. So if we were to look at our original sort of guy here, which means that this has only two significant figures the way I recorded it, that would mean that the 1 is the certain and the 7 is the uncertain place, right? That means that this measurement could be as big as 18 or as small as like 16 in terms of that error part. And if we look at where we're at, we're definitely hanging right at 17. We're actually like nowhere near 16, right? And we're nowhere near really 18. So it's really a crappy measurement you just took by doing that and lopping off that 0 pretty much in that case. When we look at this one, which is the proper way to record off of this device, that would tell us that the first two numbers here are certain numbers, and this 0 is where the uncertainty lies, which means that, this measurement might be something like 17.1, maybe it's like 16.9. And if you look at where we really are, that's really more realistic of, where the measurement is. It's within that group of error. So sometimes people think, well, it's not that important to lop off a number here or there when you take measurements, but you're really making your measurement really crappy every time you take off a number, because you're moving that level of uncertainty kind of further over to the left. Any questions on that diversion into taking proper measurements, which obviously it does depend on the device. You should always look at the device and try to figure out, really what everything means on there. Any questions on that? Okay, so keeping this sort of theme of concentration talk here, in addition to molarity, which is a very common sort of process of concentration, also really important is a lot of times we do the process of dilution. Yeah, we do the process of dilution with solutions. That kind of rhymed, I guess. Dilution with solutions a lot in this class. And when we do a dilution, you might remember a couple of equations. M1V1 is equal to M2V2. That's an equation we use a lot. And that's basically the molarity times the volume equals the molarity times the volume. This is typically your less concentrated, I'm sorry, again. That's typically your more concentrated solution. And these guys on this side is your more dilute solution. Now, maybe you learned C1V1 equals C2V2. That's good. That's all new age and all that good stuff. But the C is really just, concentration. Because really, it doesn't necessarily have to be molarity. You could use percent mass to mass, percent mass volume. You can use any concentration you want and this equation. But most of the time, people kind of go with this equation here because, again, molarity is sort of the most common unit of concentration that is commonly used. So we oftentimes will sort of use this guy. So what does that mean? Well, it means when, for example, let's say we had a bottle sitting here that's 19 molar sodium hydroxide. And we want to make a new sort of bottle that is, we'll go 125 milliliters of, I don't know, we'll just make up some numbers here, 0. It's going to be way too much. We'll go a smaller number maybe. We'll go with 7.5 molar sodium hydroxide. So we basically want to make 125 milliliters of a 7.5 molar sodium hydroxide solution. That is less concentrated, right? This is kind of your stronger bottle. This is your less concentrated bottle. So if we just kind of think about this technically would be M1. This would be V2, which is our goal. This would be M2. So basically the only thing we're missing is V1. So we would solve for V1, which would be M2V2 over M1. Now, when we do use this sort of dilution equation, you actually don't need to convert, if you don't want to, the milliliters to liters. You can if you want, but you don't have to. And that's because if I leave everything in milliliters, I will end up with milliliters. And I'll show you that. So if I put my M2 in here, that is 7.5 molar. My V2 is 125 milliliters. Let's see how I did on my made up number here. So because I didn't convert it to liters here, which again, you absolutely could convert it to liters, it will be okay because the molarity here and the molarity here will cancel and we'll be left with milliliters at the end. If you want to convert it to liters, you can, but when you're using the dilution equation, you really don't have to convert it to liters. You can leave it in milliliters. So we take 7.5 times 125 divided by a 19. I end up with something like, we'll call it 49 milliliters, right? So what does that 49 milliliters really represent? And that's something, again, people maybe don't understand. When I calculate that 45 milliliters, what I just calculated is I'm going to go to this bottle over here, And that is how much of the more concentrated solution I need to take out and put into my new container. So what I would do is take out of here into here 49 milliliters of my sodium hydroxide that I took from my more concentrated solution. Now, what is the rest of it? The rest of it should probably be, in a lot of cases, water. So I would fill the rest with water. But how much water would I put in there? Would I put in there 125 milliliters of water with my 49? And the answer is no, because if you put 125 milliliters of water in there with 49 milliliters, let me grab my calculator just to make sure, but you will end up with 174 milliliters of total volume, which is not what you're looking for. So if you just then dumped in 125 milliliters of water, you did not make the solution you were trying to make. So how do I find out how much water? So usually the volume of water is basically V2 minus V1. So I want to end up with 125 milliliters. I already threw in there 49 milliliters. That means I need to toss in there 76 milliliters of water. With my 49 milliliters of sodium hydroxide. And that gives me a grand total of 125 milliliters. That means at that point, when you mix it, which you should, you then should end up with a solution that has a molarity of 7.5. Any questions on any part of that sort of calculation? That is definitely a calculation we do a lot, super lot in here, yes. Any questions on that calculation there? So we do a lot of dilutions, and sometimes people don't really visualize, that they're doing a dilution, because sometimes I think, maybe students and people are looking for the keyword of you're doing a dilution. And sometimes that really doesn't happen. So sometimes in instructions, especially in the lab part, they don't sometimes straight out tell you, hey, you're doing a dilution right now with blinking lights. It'd be nice if they did, but they don't really do that all that often. So for example, a very common thing that we oftentimes will do in experiments is, you'll have the traditional table here where, hey, you're going to make test tube 1, 2, 3, 4, 5, however many. And, you got, we're going to take 0.1 molar. I want to use here. We'll use something. We'll do like chromium 2 nitrate. And you're going to also put in there maybe with the chromium, what we want to put in there with it? We'll put some ammonia. Why not? We're going to put in there 4 molar NH3, and we're going to add some deionized water to the whole thing. Just making this up, probably won't work, but we got something like this, and it's like, hey, test tube 1, you threw in there 5 milliliters of that, you put in there like 2 milliliters of this guy, and you put in there like 3 milliliters of this guy. So basically, if we just look at, say, test tube 1, right, you may look at this and go, well, I'm not really doing a dilution, I'm just kind of throwing all these things in. But what is happening when you do that? So you start with your 5 milliliters into your test tube, then you dump your 2 milliliters in there, and then you dump your 3 milliliters. Is you're actually doing a dilution when you're making a test tube of solution, right? And the reason for that is really because molarity is moles of solute divided by liters of solution. So what is changing as you keep dumping all these reagents into the same test tube is your liters of solution is changing, which means your molarity is changing as well. So we're doing a lot of that sort of dilution. So believe it or not, sometimes people, when they're asked, what is the concentration And by the way, those brackets mean concentration. And usually what that means is molarity we're talking about. They're asked, hey, what is the concentration of CrNO3 in your test tube, in test tube 1? And it's very common people will say, well, it's 0.1 molar, right? Because that's what it says right there. It's at the top, right? It's 0.1 molar. And again, it's not really 0.1 molar. It might be at this point where you dump it in there and you stop and you don't put anything else in there with it. But as you start dumping more in, again, you're starting to dilute this down because these are all really water environments. It's all sort of water basically that you're adding. So this is actually a dilution problem where you would need to use something like the dilution equation that we just talked about, M1V1 equals M2V2. So what would M1 be in this case? Well, M1 would actually be this number here. This is like the bottle that you grabbed off the shelf. What would what would V1 be? V1 would be how much of it that you actually used in this case. And M2 is really what you're looking for. What is the concentration in that mixture? So V2 is actually the total volume that went in there. So in this particular case, we took 5 milliliters, then added 2 milliliters, added 3 milliliters. 10 milliliters is our total volume. So what that allows us to do is solve for M2, which would be M1V1 divided by V2. Again, here you do not have to convert it to liters. If you want to, you can. And we'll see how I did in my made up numbers here. So 0.1 times, we use 5 milliliters of it, and we divided it by a grand total of 10 milliliters. Again, the milliliters will cancel, which is why you don't have to worry about converting here. And again, in my made up sort of deal here, we end up with 0.05 molar. I'll go with 1 since I did bad sig figs on all these, molar of our CrNO3 2. So you can see that our concentration of the chromium 2 nitrate started at 0.1 molar, but by just the process of adding all these other solutions into the same test tube, it actually diluted it down to 0.05 molar. And that would represent the concentration of the chromium 2 nitrate in that test tube after it's mixed. Any questions on that? Now, that is something that we see a lot of experiments. You're given a lot of these tables. You need to figure out the concentrations of everybody in the test tube, basically, in a lot of the cases, not just like you took it off the shelf. So again, it doesn't mention anything about doing a dilution, but just the process of actually making a solution is basically diluting it. Any questions on that? You obviously could do that for everybody else there. You could do it for the NH3. It would be working the same way as well. Okay. So that is definitely a calculation that we see a lot throughout the semester. And again, that's something that, they hopefully should have kind of taught you there in 50, but they might not have, hopefully, unfortunately. But it is really something that, you should really be coming into sort of this class with sort of this knowledge. So, and again, if you didn't maybe learn a lot about it in 50 based on whoever you had, or it's been a while, these are definitely this part here. You do want to kind of review some of this stuff here. It will be very beneficial to you. While we're talking about molarity and sort of ionic compounds, let's talk about another important sort of relationship that we do see in this class as well, in the aspect of sort of molarity and concentration. So I'll just use the number I just calculated, which was, I think, 0.05. I'll add an extra 0 just for fun. Let's say we had a 0.05 molar solution of, I think I did chromium 2 nitrate here. Right? Now, sometimes we're interested not in the entire substance. Because it's an ionic compound, we may be interested in, what is the concentration of the chromium ion that's present in that solution? Maybe we're curious about what the concentration of the nitrate ion would be floating around in that solution. By the way, again, a reminder that this is an ionic compound, which means when it goes for a swim, it's basically going to break apart into ions, right? Floating around in that solution. So sometimes we're not really interested in one versus the other. We just want, what is that guy floating around? So we can take something that's ionic, and when it breaks apart, like this guy here, again, it would break apart into one chromium ion with a positive 2 charge, and we would actually get 2 nitrate ions. So how does that sort of affect concentration? Well, if this guy is 0.05 molar altogether, and we were interested in just the chromium part of it, we could kind of use like stoichiometry. This is a 1-to-1 relationship, which means the concentration of just the chromium would be 1 times that concentration, which means if we were just talking about just the concentration of those chromium ions that are floating around in that solution, it would have a concentration of 0.05 molar. But if we were to relate that to the nitrate ions, it's a 1-to-2 relationship in terms of how it breaks apart, which means what we do in terms of the concentration is take 2 times that concentration of the whole thing. And it would tell us that the concentration of the nitrate ions that are floating around is actually 0.1 molar, which makes sense based on what we're seeing. We get twice as many nitrates, right, than we do chromium ions. So this is also a very important thing that we deal with a lot is we're given oftentimes the concentration of the entire thing, but we're interested in maybe just one part of it, not the entire thing. So knowing that sort of relationship between, how molarity relates to ions in a solution is very, very important. If it broke apart into 3 ions, you times it by 3. Broke apart into 4, you times it by 4. That is sort of the short version, just to show you real quick the longer what's really happening here. It really is a stoichiometry problem. We're really starting with 0.05 moles of CrNO3 2 per liter. And that's basically just this number. And if we just do it for nitrate, for example, we see that for every 1 mole, just like in stoichiometry, of the whole thing, we get 2 moles of the nitrate. Moles of the whole thing cancel, leaves us moles of nitrate per liter, which is molarity, and that's essentially what we just did. 0.05 times 2 gets us 0.1 moles of nitrate per liter. So that's really the long version of what we just did, but the quicker way is times it by the coefficient. But ultimately, that's really what we're doing when we times it by the coefficient, is really like a stoichiometry problem where we're taking it from, the whole thing, moles of the whole thing, to moles of the individual ions. Question on that? So again, like I said, that is definitely something that we do come across a lot in this class, and especially in the lab part, we come across it a lot. Any questions on that there? And I kind of talked about it, but just to make sure everybody sort of understands what I was saying about sometimes you could convert it to liters, sometimes you don't need to convert it to liters. So when you take molarity, most of the time, most people think of it as moles per liter. Another way you could think of molarity is millimoles per milliliter. So that is another sort of way that molarity works. And why it's the same thing? Because if you take milli on top and milli on the bottom, they cancel, and you end up with moles per liter. So you end up with the same thing. So when we actually do take milliliters times molarity, we are actually not ending up with moles. We're actually ending up with what are known as millimoles. And then if you take those millimoles again and divide it by milliliters, those guys essentially cancel out and come back to moles per liter. So that's why when we do that M1 V1 equals M2 V2, and we take, you know, molarity times milliliters on this side, we're technically, when we do this part of the calculation, ending up with millimoles, which is why then when we divide by that guy to the other side, we end up back to molarity, and that's why it works out okay. So you should know for sure that, though, if you happen to just multiply a molarity by milliliters, you're not getting moles, you're actually just getting millimoles. But then if you divide it by milliliters, it'll come back to molarity. So there is actually a difference, though. So if you take liters times molarity, you are getting moles. So if you take liters times molarity, you're getting straight out moles doing that conversion. So, you know, whatever you're comfortable with, sometimes it's easier for us because we do deal a lot with milliliters to not convert it to liters. But if you're comfortable converting things to liters, you could convert it to liters and convert it back. It does come out the same, just one gives you liters. But you can, a lot of times in calculations, maybe not necessarily have to always convert it to liters. You can in certain cases, especially with the dilution equation, leave it in milliliters. Any questions on that there? Okay, let me think. We did that. I think for now, that's probably enough torture here for today, I think, and reviewing. I hope this helped. I hope this hopefully reminded you of some things. And again, like I said before, if some of this stuff, you know, is not 100% familiar to you, you might want to take some time and really sort of kind of go over it again. Again, it's going to really help you. Like I said before, I'll try to post up there on Canvas a couple like review, not necessarily worksheets, but a little bit on each of these sort of topics, and it will try to help you. But definitely this last stuff here about sort of solutions, making solutions, figuring out the concentration of things in the solution, that is stuff that we will definitely see kind of over and over again. And definitely the idea, like I talked about earlier, of, you know, really being able to write these equations and reactions is really a key part here. All right, any questions on anything we talked about today, including the class or anything like that? All right, so on Thursday, we obviously will get started lecturing on chapter 12, which is kinetics. Again, the notes are up there on our Canvas site. Again, there'll be 2 fresh links to come to lecture and lab every day. So again, make sure you go through the current links